All right, so average rate of change from -7 to -6. Go ahead. -6 to -5. I think maybe something happened with your signs. It's okay. -5 to -4. -5. Sorry, it's okay. What'd you get?
43.
Yeah. -4 to -3.
13.
Good. -3 to -2. Thank you. It's okay. -2 to -1. It's -29. Okay, so when I'm hearing some negatives and positives that are wrong. It's okay. So when you do the average rate of change, you're doing the change in y over the change in x. And so all of these x's are changing by 1. So if you're trying to figure out the change in y, if you can't do it in your head, take 1 and subtract the previous one from it. All right, and then let's see, -1 to 0. Thank you. 0 to 1. Nice. 1 to 2. Good. 2 to 3. Good job. 3 to 4. We'll come back. All right. 4 to 5.
-11.
Good. 5 to 6. 5 to 6. Sorry, you're good. 6 to 7. Good. 7 to 8. Good. 8 to 9. Nice job. All right. Good. All right. So before we get to the other cards, I'm going to start highlighting these average rates to change. So when we start off, we're going from 121 to 79. Is that number increasing or decreasing? Decreasing. So I'm going to start highlighting. You guys tell me when these numbers stop decreasing. Okay. So this is where the average rate of change is decreasing. Because those numbers are getting smaller, smaller, smaller. All right. Then we start from -47 to -41. Is that increasing? Yeah. So let me know whenever we stop increasing. All the way to the end. All right. Now, if I highlighted those values on the graph, so starting at -7, the average rate of change is increasing all the way until I get to 1. All right. And then starting at 1, the average rate of change is decreasing all the way forever, actually. All right, and we'll come back to that in a second. Okay, so there was somebody who had a card that actually had both of these top ones on it. Okay, so this is about F. So where did you say F was increasing?
Did you want me to do like every single one stop or
Just from where it starts to where it stops.
so -7 to -3?
Okay, because of that arrow, we're going to go all the way to -infinity, but you're right, -3. All right, and then what else?
3 start, yeah, 3 to infinity.
I think maybe it actually starts at 5. That's okay. All right, and then decreasing?
-3 to 5.
Good. All right, so somebody had a card that said the average rate of change is positive on the intervals. What did you get?
I put the same thing as increasing.
You're absolutely right. Whoa, I can't do infinity right now. All right, those are always going to be the same. So the average rate of change is positive every time the function is increasing. That is they should 100% match. So that was good. All right, somebody had the average rate of change is negative. Good. Those are always going to be the same because that's what makes the average rate of change negative, is that the function is decreasing. So some people are having a hard time like thinking positive, negative, increasing, decreasing. So I'm trying to get that all in your head. Okay. Then we have a card that says F is concave up on the interval. What do y'all think? Or who has that? What do you think? That is 100% right. All right. Someone else has average rate of change is increasing on this interval.
I'll put 1 to 30.
That is 100% right. Because everywhere where the function is concave up, the average rate of change is increasing. So we showed that. Like we looked at the average rates of change and we saw that they were getting bigger. It lined up exactly where the function is concave up. It would help if you pay attention. All right, and then one more concave down. All right, and then the average rate of change is decreasing to 1. Good job. So again, we looked, we saw that pink area was where the average rate of change was decreasing. It lines up exactly where the function is concave up. So there are people in here that are really still struggling with what that means, that the average rate of change is increasing, and they don't believe it. But we show, like, this is really what happens on the functions when you're looking at the concavity and the average rate of change. Okay, let me give you guys your notes. All right, so we're gonna, like I said, these same things are gonna come up again and again and again. There are some new things that you are gonna learn today we haven't talked about yet. One of those is the absolute or global extrema, so absolute or global max and min, and points of inflection. But a lot of the stuff we're talking about today is stuff we've already talked about or that you learned about in Algebra 2. So we have this very analytical, mathematical, symbolic form of a polynomial function, and it looks very overwhelming. But this is a representation of a polynomial function. N is a positive integer. So I'm going to add something to that. So N is 0 or a positive integer, because 0 is not a positive integer. Okay, so what is not 0 and not a positive integer? So what's something that's not a positive integer? Negative. So any negatives, that cannot happen. So n represents all of these exponents. So if it's a polynomial function, you cannot have a negative exponent. What else is not a positive integer? What's not an integer? A fraction or a decimal. Your exponents cannot be fractions or decimals for it to be a polynomial function. And then what about if your exponent is a variable? So let's say you have like 3 to the x. Is that okay for a polynomial function? Is x an integer? No, x is a variable. X, when you put that x as something, or it can be any number. So that is not going to be okay either. So you can't have a variable as an exponent. You can't have a negative. You can't have any fractions or decimals for it to be polynomial. All right, a sub I, which represents all the coefficients, cannot be, it has to be a real number. Now you guys are the first Algebra 2 class that, since I've been teaching, that did not learn about imaginary numbers. And we're going to learn about them next week. So any number that you've ever heard of your whole life is a real number. So it's fine. So pi. Is pi a real number? Yeah, it's 3.14, blah, 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 blah. There's another number that's e. It's called Euler's number. Euler is that guy in the red back there. Is e a real number? You learned about it when you learned about exponential growth. It is. So it's like 2 point something, something, something. That's a real number. They're just variables representing numbers. So those are real numbers. Any decimal is a real number, any fraction, anything. So pretty much any number you've ever heard of, it can be a coefficient. Okay, so the leading term of a polynomial function is going to be, in this case, it's a sub n times x to the n. Which one of those is going to be the degree? The coefficient or the exponent? N, yes. N is the degree. So the largest exponent is the degree of a polynomial function. And then the number in front of the variable with the largest exponent is the leading coefficient. I feel like you probably remember that from last year. All right, so in example 1, we have all these polynomial functions. Their exponents check out, their coefficients check out. So what is the leading coefficient of this first one? 3. And the degree? 4. Nice job. All right, this one is slightly more challenging because the order is a little bit mixed up. So what is your leading coefficient? Good. And your degree? Nice. All right, what about this one? 4. And the degree? 0. So if the degree is 1, it would have been like x, because that's x to the first. So no variable at all, the degree is 0. It's okay. All right. One thing that you guys learned about in Algebra 2 were local maximum and minimum values. So I think you spent a lot of time talking about that. There is another type. So there are 2 types of extrema. Relative or local extrema, like what you learned about before. And there's also absolute or global extrema. So let's talk about this local extrema. Local or relative extrema occur when a function changes from increasing to decreasing or decreasing to increasing. That's going to be at the top of the mountains or the bottom of the valleys. Also, a local extrema can occur at an endpoint. I'm not sure if you learned that in Algebra 2 or not. So this right here is an endpoint. On the other side, it's an arrow. So my eyesight isn't great right now. So every arrow, I'm making sure I see that it's an arrow. Okay, so what x values is there a local minimum? -4. That's this one right here. And what else? 0. It looks about 0. It might be a little off. All right, what about local maximums? Good. Those are those. All right, and then absolute extrema sound exactly what it sounds like. They are exactly what they sound like. The absolute highest or the absolute lowest the function reaches. All right, so this one, again, this is the same graph. There's an arrow. So the question is asked a little different. So it's asking what is the absolute maximum value? So what do you guys think about this one? 2. That's the y. That's the highest it reaches. And then where does that occur? What x? Good job. What do you guys think about absolute minimum? There doesn't have to be one, by the way. Negative infinity is not ever going to be an answer, but he's right. It does keep going down to negative infinity. So do you think there is an absolute minimum? There is not. So if the answer to that, if you want to say infinity or negative infinity, the answer to that question, that means there's not one. And there doesn't have to be. There doesn't have to be any of these, actually. All right, so let's do one together. Then I'm going to have you guys try some on your own. Oh, it says to write in A. I've been writing none. It doesn't matter. Okay, so we have this polynomial function. What do you guys think about relative minimum? Is there a relative minimum? No. What about relative maximum? Yeah, it's when x is 1. And about absolute minimum? None. So if there is no relative minimum, whoops, I'm going to try to follow directions, but I don't want to. If there is no relative minimum, there's not going to be an absolute minimum. All right, what about absolute maximum? Good. Nice job. All right, so you guys try B and C on your own. I'm going to come around and grab those little cards, unless you want to keep them for some sentimental reason. I'm just going to throw them away for you. All right, so check yourself. It's okay if you messed a number up. Sometimes you don't see like the actual arrow and think there is a minimum when there's not. All right, any questions on those items? All right, so let's look at some fun facts. These are fun facts, but they also are actual standards where they might create some kind of question to see if you know these fun facts. So between any two real zeros of a polynomial, so zeros are basically x-intercepts where the function is 0. So that's 2 zeros. That's 2 zeros. Here's 2 zeros. So between any two zeros, there has to be either a relative minimum or a relative maximum for that to happen on a polynomial function. So there must be at least one local maximum or local minimum. And then polynomials of an even degree. So if we look at A up here, that's a polynomial with an even degree. So that degree probably is 2, so it looks like a quadratic to me. But it could be a quartic. So anyway, for sure, the even is an even degree. So even degree must have either a global maximum or global minimum. Now don't turn the page yet. We're going to go a little more detail. Alright, so that one up at A, let's say it's a quadratic. It's an upside down quadratic. What makes the quadratic be upside down, open downward? The negative in the front. So a negative leading coefficient. So for there to be a global maximum with an even degree, there also has to be a negative leading coefficient. And so all even degree polynomials are gonna kind of look like parabolas. They can have some extra humps depending on what the degree is and how the function works. But they're gonna have the same basic shape. So for there to be a global minimum, it would need to be like a upward facing parabola, which means there's a positive leading coefficient. All right, and then the last new thing we're going to talk about today are points of inflection. So points of inflection occur when a function changes concavity. So changes from concave up to concave down or vice versa. And also at the point of inflection, the rate of change changes from increasing to decreasing or decreasing to increasing. So I'm going to scroll back to the one we did at the beginning. What x value would there be a point of inflection on this one? That's where, because remember the pink was the concave down or the average rate of change decreasing. The blue was concave up. So that's the point where the concavity changes. Now, a lot of times we're just going to have to guess what it looks like. If you guys take calculus, we'll actually make sure we find the right x value, but I think you'll be fine for what we're doing here. All right, so when this graph starts being a graph, is it concave up or concave down? Concave up. And where does it stop being concave up, does it look like?
-1.
When x is -1, good. All right, then the graph changes to concave down for just a little bit. And when does it change again? +1. Those are the x values. Those are the x values of the points of inflection. So it's just a new word to learn. Points of inflection. But you pretty much already understand concavity, so I don't think it's going to be like super, super hard for you. All right, now to save on time, we are not going to write really beautiful sentences right now because I want you guys to have some time to work. And so on these ones, we have these intervals. We're going back to this graph, and we want to know where the rate of change is increasing or decreasing on these intervals, or if the rate of change is increasing or decreasing. And then we're going to give the reasoning. So like I said, we're not going to do super beautiful wording here. So let's look at 3 to 4. On the interval from 3 to 4, this is this section right here. Whoops, there's not an arrow. Would you say the rate of change is increasing or decreasing there? Increasing. Why? Not a positive slope. Concave up. So when you're deciding if the rate of change is increasing or decreasing, it is concavity has to be the reason. So g of x is concave up. All right, let's look at -4 to -3. So this from here to here. Is the rate of change increasing or decreasing? Increasing. Why? There you go. All right, you guys try 3 and 4 on your own, please. All right, what do you guys think about 3? The rate of change? Good. And the reason? Nice. and then 1 to 2. Nice job. All right, you're getting there. You guys can do this. All right, now my last class,